So, hello, welcome everybody, and welcome to my little talk. I wanted to say one thing first, and this would be Lehman Kao. When I was at the university, I had the big pleasure to study Mandarin Chinese and Chinese arts for one semester. I enjoyed that very much. So, welcome. My name is Reto. I am unable to use a computer properly, obviously. Yes, okay. Yeah, I used to be a programmer, but programming is actually pretty boring, I guess. Okay, so what is cybernetics? There is one misunderstanding about cybernetics, which is, I would say, pretty old. Cybernetics should have something to do with the internet, which is not true. The internet is in itself a cybernetic system, yet a cybernetic system is not necessarily about the internet. The word comes from ancient Greece, and it means Kybernetes, which means the helmsman, the person who steers a boat or a big ship. It is the one that is in control of the machine. It's machine control in this context. In ancient Rome, it was gubernator, which was the governor or mayor of a region. So that was the person who was in control of the political part in ancient Rome. And maybe sometimes today, and in medieval times, Kybernetes was the name for the worldly affairs of Christian churches. So you see, cybernetics is about control. It is about control and understanding of complex dynamic systems. And please not the internet. So a cybernetic system can have access to the internet, but does not necessarily have, right? Okay. So what is cybernetics at first? I will get the boring stuff out of the way, so I can, well, tell you about the interesting stuff. The modern term cybernetics was created by Heinz von Förster, who was a German scientist, and he was at the Josiah Macy Foundation conferences. They took place in 1948 in the United States of America, and they were designed to find, at first designed to find new medicine, new treatment possibilities for the very, very sick daughter of the man called Josiah Macy. They failed, she died. But they tried to unite scientists from all the different topics, from psychology, from philosophy, from engineering, from natural sciences, from everywhere, to find one solution for a very big problem, for a very, very sick girl. Incidentally, they failed, but after that, they did not disband. They created a new science called cybernetics. And important personalities of modern-day cybernetics, I would say, is Heinz von Förster, I said, John von Neumann, Norbert Wiener, Umberto Maturana, Warren McCulloch, Max Bense, Karl Steinbuch, William Ross Ashby, Gotthard Günther, Niklas Luhmann, Claude Shannon, and Frank Allgöwer. Frank Allgöwer was one of my professors. He still is, sort of. You see that this, like all sciences, is very, very united. It takes place in all the countries I know. It unites different sciences, mathematics and biology and medicine and philosophy and arts into one very, very interesting field. One interesting anecdote maybe would be Claude Shannon's formula for information entropy. You know, I'm not bothering you with mathematical formula, but just so you know, Claude Shannon found a mathematical term to describe how much information a signal has. Why do you need that? I mean, you usually don't care if you use your cell phone. It just, if it works, it's good. If it doesn't work, it's not good. But for this technology, for mobile technology, for mobile internet, for the internet itself, this term called information entropy is very, very important. It's for engineering, for development, and for maintaining these systems. Very important. And the idea from that came from Max Benze, who was an art theorist. It's interesting that art theory in this context really has contributed to engineering, which is something that is most unusual, I would say. But the unusual things do not stop in cybernetics. What is cybernetics now, I should say? Cybernetics is the science of the dynamic of systems, their interdependencies, and their feedback mechanisms. So, in, well, more understandable terms, cybernetics sees everything that is as a system. And everything that is can have an input or an output, or many inputs or many outputs, right? Like an animal, like a machine, like everything that is. And cybernetics is designed to understand how these systems interact and how they work together with each other. An example for cybernetics in biology would be the analysis of leaf-cutter ants. I don't know if you're familiar with them. Leaf-cutter ants have a very, very interesting way of life. They live on a big fungus, which they use as a house, as a living space, but also as food. And these leaf-cutter ants, they go out and cut leaves. They find leaves and cut them and bring them back. Then they chew them and they feed the fungus, so the fungus grows, so they still have a house and they have something to eat, which is, I would say, a form of farming. It really is farming. And the interesting part of that is, a single ant has absolutely no idea what it is doing. It does not know anything about it. But it still behaves very smartly in the group. And this is called swarm intelligence. It is a topic that is being analyzed in cybernetics a lot. So if you want to understand this behavior of the ants, a cybernetic perspective might be a good one. I'm not saying this is the only way. I say it is a way I like best. Cybernetics is a meta-science. It is not purely focused on a specific brand of scientific thinking. There are cybernetic fields in the sciences of engineering, which is engineering science, engineering cybernetics, like Frank Algöver, John von Neumann, and psychology, by the way, and cognitive theory. There's also a cybernetic field, like one of the persons is McLuhan or Niklas Luhmann. So if you think about systems like a psychological system, a personality sort of can be seen also as a system, which is not very romantic, I believe, but it sometimes helps to take in this perspective to understand mental problems like depression or something better. I'm not saying cybernetics would be superior to any science. I would say they're a valuable asset, an interesting and helpful way of thinking. There is cybernetics in biology, for example, in Norbert Wiener. In art theory, Bruno Latour, for example, Peter Weibel, Hans Runge, and some others. Neural networks. Warren McCulloch is one of the first who made artificial neural networks. What do you need neural networks for? They're not just some boring mathematical theory. Okay, they are a very boring mathematical theory, but they make very interesting things. So, for example, when I close this PC and I open it, I don't have to enter a password. It has a camera and it detects my face. It does not only detect that it is a face, it detects my face. And if another person would sit in front of this computer, the computer would know it is not me, so it would not unlock it. And that is done via artificial neural networks. They are an attempt to model neural systems like the human brain or neural systems of other living beings. They are not at all as strong as real biological systems. They are not at all as smart, not even remotely, but sometimes they can be a helpful asset. Very modern cars, for example, also have cameras that find street signs and maybe can give you an information if you're driving too fast. Because the camera saw... Do you have a question? Okay, so please, if you have any question, you can also ask at any time. Okay, so yeah, it detects street signs, maybe speeding information, and it can tell you if you're driving too fast or not. That is done with neural networks, which are influenced by also by cybernetics. That's a good one. So, what is this science really? It describes feedback systems also, their behavior and their impact on other systems. So what does feedback mean? It means a control system that gets feedback on its own results. So for example, a thermostat would be a very simple cybernetic system. Right? A thermostat is designed to keep a room or a baking oven or anything like that at a certain temperature. So the oven needs to, or the room or the heating needs to know how hot is it, and if it is too hot it stops heating, and if it is too cold it starts heating. That's feedback, and that is very essential to cybernetics. Also, this is a very simple and not very interesting part, but it is very important. When studying cybernetics, there's one downside. You would have to study a lot of math. But anyway, I think it is worth it. Obviously, every natural system can be considered cybernetic, as I said, because it has inputs and outputs and interacts with others. So when I was talking about the leafcutter ants, they are a swarm. One ant does not know what it is supposed to do, but the whole swarm behaves correctly. That's called. And also they have different types of ants. Some are workers, some get the leaves, some others clean up, and so on. And this swarm theory, for example, is not only just for fun, although I think it is a lot of fun. It is also to understand. It's also helpful to understand people, for example. Some years ago, there was a very terrible tragedy, I think it was in London, England, when in a discotheque, a fire broke out. And the people wanted to get out. And they built a swarm, but they were so many that they clogged the doors, and many people got injured heavily. After that, they applied swarm theory to change the layout of this discotheque building. So if a fire would break out again, the people could all get out and not get hurt. So these interesting topics are, I would say, are really also useful for something, right? There is nothing that does not influence something, and on the other hand, there is nothing that is not influenced by something. This guy, for example, has only one arm, and he has a robotic. He got a robotic arm with which he can not play the piano, but with which he can grab and do things like if he had a real arm. This technology is called a robotic arm using myoelectric sensors. Myoelectric sensors means there are electrical sensors that detect very small electrical currents in the body. If you are moving, if you're moving or using your muscles, they are controlled by electrochemical impulses. That's known today. And if the arm is missing, the nerve signals still reach the arm. So if you measure those signals, you could tell a robotic arm how to move. This technology is far from perfected, but still it works. And I'm showing you a small movie about it. So that is really interesting to me, at least, because it has a lot of engineering components in it. It of course has those sensors I was talking about. It has motors. It has control, because the motors need to be controlled very precisely. Because you see, we have what is called in mechanical engineering a kinematic system, which means my upper arm is of course connected to my lower arm, so if my upper arm moves, the lower arm moves with it because we're stuck to it, right? And then the hand and the fingers. And this movement is very, very complex, so in order to make it seem at least a little bit natural, there are very, very complicated mathematical models that need to be implemented in those microcomputers that are controlling those movements. But you see, it was quite precise. It wasn't. I mean, the first one was a little bit funny because when I saw it the first time, I was happy for the guy that his coffee cup had the top, you know, because the arm was too fast and maybe his coffee would have landed in his face. But still, as I said, the technology is not perfected yet. And it will take some time until it is really perfect. And I don't know if it ever will be perfect, but then we engineers would have nothing to do left, right? So, but still, when he was trying to catch the little piece of cloth, it was very, very exact. And now, they also have technology that can give you feedback. It's just the example for a lost limb, but there are other examples, of course. They give feedback, so the problem with a robotic arm is if you touch something, you don't feel anything because you don't have nerves, like if you have a normal arm, right? But now they also have mechanical sensors that give you little impulses, little electrical impulses to where the robotic arm is connected, so you really can learn to feel a little bit again. And I think that's really an exciting topic. By the way, there are also robotic legs for people who have lost their legs, for example. And maybe you know, there's like something like the Olympic Games, but also something like the Olympic Games for people who are disabled. And one day I learned that a person without a real, with only one leg, who had lost the other leg in an accident, he wanted to participate in running exercises in the normal Olympics, but they wouldn't allow him for one reason, because he's simply faster with the robotic legs than a normal person, because the robotic legs have motors and batteries, and you don't need muscles for that. It's interesting. I don't say you should replace your natural limbs, but if you have the very big misfortune to lose one, which I hope for nobody, but in that case there will be sort of replacement. What is cybernetics again? Question. It is not only about robots, but it's about its own control of technology. This one is a really cool example. It's a walking robot. It's not a man in a suit, it's a robot. It's not a movie, it's really a film of technology. You see, you already can see and feel obstacles and go over obstacles. It does not fall down. I mean, sort of not fall down, right? It looks a little bit clumsy though, but still, it's a walking robot, right? And in order for that to work, for that technology to work, a lot of things have to be done. I said cybernetics is about control also. I mean about controlling disease, it could be. But in that case, it is about controlling the machine and preventing that it falls down. For that, it also has to have a feedback. It has to have a sensor that tells the robot which direction he is facing. If he's maybe on the wrong side, or maybe he's staggering, so the robot needs to know that. We humans have that too. We have in our inner ear, we have sensors that help us stabilize and help us see whether we are upright or not. Even if you close your eyes and tilt your head to the side, you know it's on the side, right? And that is why if you're in a swing or something, you can get dizzy because that organ gets confused, so you might fall down. That's when the feedback does not work anymore. Another thing, that's great. Conway's artificial life. I was talking about swarms like ants or bees. By the way, I forgot to tell you. There's also a very interesting technology where they analyzed the behavior of bees. They put bees on a field where there were no flowers, where they could get some nectar. And then they put on this field several places where there was sugar water. And the bees were looking for the sugar water. And they gave the bees some sensors so the scientists knew where the bees were and how the bees were flying. And they wanted to understand better how a bee swarm works, how a bee swarm behaves. And I would say, although a single bee would not be very smart, the whole swarm is very, very smart. And the remarkable thing was, they put the bees, they put that places where the sugar water was on several parts on the field. And at first, the bees, the searcher bees, they have like bees that are specialists for looking for flowers. And at first, they flew around in random, and then they found places, and then they went back. And each time they went back to the sugar water, their path was more optimal, their path was shorter. They did not take as many detours as the last time. More and more, they get more and more optimal. It's called optimal in cybernetics. The interesting thing is, they solved a problem that has not been generally solved in mathematics to this day. It's called the traveling salesman problem. Imagine a salesman who has to travel a lot and to meet customers and sell his goods. He wants to take the shortest route to the customers. Because, I mean, if he has a long route, it's more expensive and takes more time, sure. But that, to find, or to automatically find the shortest route to take is very, very difficult. And the bees, who were considered quite stupid, really found it, which is remarkable, I guess. Conway's artificial life is a simulation. it is not not a simulation of a real biological system. It is a very simple version of a swarm theory, a hypothetical, or maybe an artificial swarm. But this swarm is not very interesting. But it has very interesting behavior. Just imagine these little dots here. Consider them like cells. It's called a cellular automaton because it somehow resembles how cells work. One black dot is a cell, and a white space is just nothing. There is just no cell. And the rules are this. If one black cell has two neighbors, the cell stays. If it has less or two neighbors, or more than three, the cell dies. And if if one place has exactly three neighbors, then it will get born. The idea behind it is to simulate something that behaves a little bit like bacteria, which are cells, right? The bacteria, if it has not enough neighbors, it would die, maybe because of loneliness or because a single organism cannot survive alone, which is not quite true for bacteria, but let's just say it is now. If it has less than or more than three, it's just too many, so the cell cannot survive. If it has three, it's optimal, so it can get born. That's just the idea. And just if you apply those rules here to this example, I'll show you a better example later, but to this example, this happens. It's the first part, and then the second part looks like this because these new spots have three neighbors when they get born. Next one will adapt because some spots have too many neighbors, so they all die. Oh, sorry. Okay, fourth looks like that, and just look at that that sequence. That's how the simulation works for 10 black dots in a row. Now I have a better simulation. I wrote a little program more than a decade ago where you can simulate that. Yeah, it works. So you can just imagine those are the living parts, and you can paint some if you want. Paint some, whatever, and run the simulation. See, this is called a floater. This system sustains itself. It doesn't grow, it doesn't die, it just moves around. And after some time, maybe it collides with something, building another complex structure and others. So I think that's quite an interesting idea. It's not my invention, it's invented by John Holton Conway, and as far as I know, it's the first working artificial life simulation. And you can easily program that. It's just like in one afternoon or something. Just look how it automatically behaves. It's only those rules I told you, only those 3 or 4 rules that make all this happen. And these ideas are used to try to understand how life works. Because out of a single cell, a whole animal can grow. Out of a single information, a whole animal can come to be. So yeah, that's it. That's not, I mean, it goes on forever, and we could make some more. For example, if I think those guys are lazy, I can paint some more guys in there, and suddenly they change behavior. Right? Those guys should get moving. I think, okay, they're lazy again. So now, see, some really don't want to do anything, but anyway, maybe it's the same like people. Okay, yeah, that's Conway's artificial life, and I wanted to show you that. Okay. I think that's quite interesting. I said that the sciences are not necessarily so sharply separated, and maybe they should not be. I guess that in the end, it is like it was until 250 years ago, where people studied science and then decided whether they wanted to go in medicine or law or philosophy or something. Cybernetics has also a lot to do with art, because if you think about it, if it looks at systems, it also looks at artworks and artists and people who enjoy or do not enjoy art. So there's a complex dynamic there too. For example, maybe you have seen Mark Rothko's White Center. It doesn't matter. It is a famous painting by the American poet Mark Rothko. It is just four colored areas, white in the center, and it looks very, very simple. It actually isn't simple, but it looks very, very simple. But it cost about 80 million US dollars. And the question is, why does it cost so much? Because somebody was willing to pay so much for it. That's the idea behind it. So this is a cybernetic question. How does something that's sort of worthless, like a canvas and some paint, which is like, I don't know, worth $10 or 20, turn into something that is worth 80 or I think $79 million or something, but that doesn't matter really, right? So yeah, how does that happen? Because of dynamics between people who bet on auctions. This is another one, it's called Number 5 by Jackson Pollock. Maybe I can show you the images later. No, I don't have them, that doesn't matter. It cost around 150 million US dollars. It's a nice painting, but I wouldn't really pay that much. Even if I could, I wouldn't. But anyway, that's just the dynamic of systems, which is not only in engineering, but is used by engineering cybernetics. This is brain painting. It's by the artist called Adi Rüsler. I've set him down here. Adi Rüsler is, I know him personally, is really an interesting artist because he paints only using his brain. The brain can be measured and analyzed. There's, for example, functional MRIs, which is a technology that measures the oxygen content in your brain to find out which brain areas are active. And if you know that, if the doctors know that, they can figure out if everything is okay or maybe there is cancer, right? There's an easier technology or a simpler technology which is called an electroencephalogram. It is just, like a little hat that measures very rawly the workings of the brain. And it is used, for example, for diagnosis in sleeping problems. If people cannot sleep, this technology is used to, besides other things, it's used to find out why they cannot sleep. And the artist Adi Rüsler found an idea to just make it, well, paid. The data from this measurement is fed into a computer and it is trained. Also, the artist has to be trained and the computer has to be trained. So if the artist thinks, I want red, the computer notices red. And then he thinks, I want, for example, a square, but not in the middle, but like a little bit on the left, a little bit down, and then you get this part. And then you think, well, circle, I think yellow, a little bit up in the middle, and then you get this one. That's an interesting thing. You can actually paint by thinking, which is basically what a painter does too, but he goes the little detour over the arms and the brush on the canvas. But I mean, you cannot make, nowadays at least, cannot make something that would resemble a Rembrandt, I guess. But maybe, well, maybe it will be possible someday. But what is that good for? That really has a real application. It's not just for fun. It is fun, again, but it's not just for fun. It is, for example, used to help people with the so-called locked-in syndrome. There are people who are awake, fully awake, but are unable to move or to speak or to do anything. It's a very, very, very bad condition. But with this technology, can help them, for example, say words, or paint, or do something. Probably the worst fate I can think of to be locked in, where you have no ways of interacting with other people. You're really imprisoned in your own body. I don't want to scare you, sorry. It's very rare, but still, this technology can help people. That's from my house. I'll show you. Oh, sorry. What is that? It's a cleaning robot, which right now cleans my house. There was a bit nasty to it. That's not also very helpful. It is, I think, very exciting. This is a vacuum cleaner which, well, has laser sensors in its head, in that round part here, where it can detect walls and chairs and furniture and plan the route and find ways to find every place in my house and get everywhere where it can fit, of course, and clean everywhere where it gets. And also, if I stand in front of it, it just realizes, wow, there's an obstacle that wasn't there before, and it plans a route around it. And you saw maybe, it just went around in a circular or elliptical shape around my foot. That's really, really interesting and practical, very practical. Right, so these automated robots are not really commonplace, but they're not science fiction anymore. And maybe you have heard from the self-driving cars which are developed now. So you don't have to drive a car on your own. You just get in some car and tell the car where you want to go, and it drives you there, which is part of science fiction, but which is a technology that really exists now. And maybe it will be commonplace in some time. But there's a downside. Just quite recently, I have heard from a colleague of mine from our organization that there was a bad accident with a self-driving car, where the person who was inside, who was not really the driver, actually got hurt a lot. And so yeah, there's not a good idea to blindly trust technology, but still it will happen. And it is, as I believe, helpful. And I'm pretty convinced that self-driving cars, if everybody had a self-driving car, there would be by far less accidents and less traffic. Because just in this hypothetical scenario, if every car was self-driving and they were in a network, they could talk to each other and find the best route for everybody. So there would be no car stuck in traffic in the long run, I hope. Maybe it will happen, maybe it won't, I don't know. But I'm pretty sure we'll have some very exciting new technologies. Maybe as a last thing, I want to show you a little bit of one part of my own work. You can use mathematics to create paintings, which is not, of course, not very new. There were the fractals. Maybe you've heard of fractals, but that aren't fractals. There was the ancient Greek philosopher Pythagoras, who lived about 560 years before Christ, and he believed that he could use mathematics to find out what the Greek gods wanted, because he believed that the gods had some sort of harmonic idea, and he looked for those harmonies, interestingly, in math. And what did he do? He used, well, music, and by accident created music theory, European music theory. He had a block with a string and had a little block in between it, and parted the string and just found out and listened how the string then sounded. And you see, if you put the string in half, then you will have a sound step of an octave, which is in every music theory, where a line of harmony repeats itself. So yeah, Pythagoras believed that math would be helpful to understand what the Greek gods wanted. Maybe he was right, maybe he was not, but he was right in one part, that math does contain aesthetic information. Remember when I talked to you that art theorist Max Benze had an idea for a mathematical term to describe the aesthetic of an artwork. I'm not sure if he succeeded with that, but Claude Shannon then used that formula and made his own information entropy formula out of it, which is now necessary for mobile phones and mobile internet. So these crazy ideas are maybe crazy, but still very useful. So yes, the contents of a mathematical term have aesthetic properties. And what I did here is create a program, a system that translates the aesthetic information of the mathematical term into something that is visible for everybody, also those who are not very familiar with mathematics. Okay? So yeah. There's another example I want to really show you. There's for engineering, we're talking about engineering cybernetics. There's also an interesting simulation to find out whether there is something like chaos. I mean, there is chaos. And one student of me made one model, which is a so-called double pendulum. Double pendulum is just a pendulum with another pendulum on it. That's just all of it, right? And this system behaves, for some parameter configurations, chaotic. Why am I saying that? The reason for that is, for engineering, in engineering, sometimes things happen or other things do not work and nobody really knows why. Sometimes it is because there's system dynamical chaos. How do you take that with mathematical models? And I would like to show you the animation of it. If I'll find it, yes, here it is. Just takes a little time. Yeah. By the way, I thank my student Gino. He made this model. Wait a little moment. Maybe the next assignment will be to make this model run a little faster. Yeah, now it comes. Just a pendulum on another pendulum, and the blue dots here are just like masses, like iron balls or whatever, and the black ones just show the direction of movement. bad, isn't it? And that was the path one of the blue spheres was taking. So yeah, it just looks totally erratic, right? And for that, mathematical theory in cybernetics is very, very helpful. So I think that's a little bit. That should be enough for now. So thank you very much for your